Okay, so kita tengok yang ni. So this will be the next chapter, right? So this is something different, okay, based in comparison to what we have learned previously, right? So previous we have considered the serviceability limit state, okay, whereas we do not consider the factor of safety, okay, because actually the factor of safety for serviceability limit state is 1, right? So therefore we do not multiply, okay, our values of the strength of materials, okay, and also loads to any factor of safety, right? So as for the flexural resistance, okay, which is under ultimate limit state, so basically, okay, we are going to multiply, okay, and also use the factor of safety as what we have used previously in the RC structure, right? Okay, so this topic, right? So we have flexural resistance under ultimate limit state, right? So at the end of this lesson, okay, you should be able to calculate, okay, and determine the ultimate moment of resistance for the section, right? And the second one is to design the untension or conventional reinforcement if required, right? So after we have determined the ultimate moment of resistance for the section, okay, then we are going to compare with the design moment. Okay, so what is the moment that is subjected to our structure, right? That is based on, that is due to the loadings, right? Then we are going to compare, okay, with the ultimate moment of resistance, okay, that is provided by the section together with the pre-stressing tendons. Okay, then if it is not appropriate, right? So if the value under ultimate limit state is not sufficient, right? So therefore we are going to design for the untension reinforcement. Okay, right. So we move on to the next slide. So for the introduction, after a pre-stressed member, okay, has been designed to satisfy the serviceability requirements, a check must be carried out to ensure that the ultimate moment of resistance and shear resistance are adequate to satisfy the requirements of the ultimate limit state ULS, right? Okay, so the ones that we have already determined earlier, okay, whereas we have designed the pre-stressing tendons, right? So we have considered the design of those tendons under serviceability requirements, right, under SLS. So now, okay, we are going to go towards the ultimate limit state, and we are going to have two resistance, okay, that we have to consider, which are the ultimate moment of resistance and also the shear resistance. Okay, but as for today, we are going to go for the flexural resistance first, okay, whereas we consider the moment. Okay, then the FOS, okay, or factor of safety, okay, considered are similar to RC design. Okay, whereas if we are to calculate the value of the design moment, right, so therefore we are going to consider, okay, those a factor of safety of 1.35 kgk plus with 1.5 qk, right? Okay, so the factor of safety, right? So the factor of safety are 1.3 and also 1.5, right? So it is similar to the RC design, okay, because this factor of safety, okay, is not only particularly for RC design, okay, but it is also for for the ultimate limit state, right? Okay, so when we are calculating for the ultimate moment, design moment, okay, so therefore we are going to use this factor of safety as well. Okay, so with additional consideration of the pre-stress force effect, right? Okay, so if we are considering only RC structure, okay, we do not have any pre-stressing reinforcement, right? So therefore, we do not need to consider this. But as for a pre-stressed concrete structure, okay, we are going to have one additional partial factor of safety. Okay, so this is the partial factor of safety for material. Okay, whereas we are considering the pre-stressing steel, okay, with the partial factor of safety of 0.9, right? So saya change sekejap, saya change the color of the pen. Mana pula? Okay, okay, pen color. Okay, so I change it to blue lah. Okay, right, so we have this partial factor of safety, right, so which is 0.9. And when we talk about this partial factor of safety, this is the partial factor of safety for material, right? So we are going to multiply this, okay, with the strength of our pre-stressing steel, right? So the pre-stress force is considered as favorable effect. Right. So the analysis of section, right? So as loads in the pre-stressed member increase above working values, okay, the cracking occurs and the pre-stressing steel begins to behave as conventional reinforcements, okay, whereas it will take the tensile forces, right? Okay, so previously, okay, when we learned about the pre-stressing force, okay, or the pre-stressing steel under serviceability limit state, okay, we know that this pre-stressing steel is meant to induce the compressive stress, right, or compressive force to our structure. However, okay, when we are talking about the ultimate limit state, okay, whereas now our beam section is already under flexural behavior, right? So therefore, it is prone to cracking, right? So when it is prone to cracking, it means that our beam actually bends in the similar way as a reinforced concrete structure with this pre-stressing tendon, okay, acting almost like the conventional reinforcement, right? So we know that when we talk about conventional reinforcement, the function of this conventional reinforcement is to cater for the tensile forces, right? Okay, so similarly here, okay, we are considering, okay, that our pre-stressing steel is taking the tensile forces. Okay, so the behavior of the member, okay, at ULS is exactly similar to the ordinary RC member, with additional additional initial strain in the steel must be considered in the calculation, right? Okay, so we are going to have additional initial strain that is um, subjected, okay, to our pre-stressing steel, right? So this analysis, okay, can be done using the equivalent stress block, right? So the equivalent stress block, okay, is the same equivalent stress block that we have used for an RC structure, okay, in the analysis of sections, right? So you can see here, this is the stress block. Right, so basically we are going to use the similar stress block for our section, right? So we are going to use the uh, similar equilibrium equation, right? Okay, so for the analysis of section, okay, it is giving us the equivalent stress block, okay, which can be applied to a cross section of any shape, okay, which may have an arrangement of pre-stressing wires or tendons, right? Okay, so it can be of a flange section, okay, or it can be of an L section, right? Okay, so we can use a similar equivalent stress block, okay, in order to analyze the section, okay, and determine the moment of resistance for our structure. Okay, so the stress strain curve, okay, for the pre-stressing steel, okay, is used to calculate the tension forces in each layer of steel, right? Okay, so we are going to look into, okay, the arrangement of the pre-stressing steel in our structure, okay, whether, okay, we have one or two layers of reinforcements, okay. Then we are going to calculate also for the total steel strain, okay, which is due to bending and also due to the initial strain, okay, which is due to the pre-stress basically, right? So for a series of assumed neutral axis positions, okay, the total tension capacity is then compared, okay, to the compressive force developed by a uniform stress of 0.567 FCK, right? And the moment from there, the moment of resistance can be evaluated, right? So basically we are going to calculate the value of mu here, okay, and this uniform stress, okay, is actually for the concrete, right? When we talk about 0.567 FCK, means that we are now referring to the concrete strength, okay, right? So as you can see here on our left, right, so we have the a typical stress strain diagram, okay, that is for the pre-stressing steel, okay. And when we talk about pre-stressing steel, okay, we are going to use the value of the proof stress, okay, whereas this proof stress is determined, okay, based on this 0.1% offset, right? So if we are talking about a normal steel, okay, or conventional reinforcements, okay, usually we are going to refer to FYK, right? So for FYK, okay, the offset value is 0.2%, right? Okay, which is this value. Okay, however, when we talk about pre-stressing steel, okay, the offset value here is 0.1%, okay, which is known, okay, as the proof stress, right? So this is considered as the proof stress, okay, whereas we are considering, okay, that at this point, okay, the section the steel pre-stressing steel yielded at this point, right? So this will be the yield point, right? So you can see that we have here, this is the simplified version, okay, of our stress strain diagram, okay. And as for this type of steel, okay, that we are referring to, okay, the value of E, okay, for the pre-stressing steel, okay, is 205 kilonewton per millimeter square, okay. And we can see here, okay, that at the yield point, okay, we have this proof stress, okay. And similar to the conventional reinforcement, we also have to consider the partial factor of safety for steel, right? Or partial factor of safety for material. And as for the steel partial factor of safety for steel, okay, for conventional reinforcement and also for pre-stressing steel, okay, the value of this gamma m, okay, is equals to 1.15, right? Okay, so it is similar, okay, to the conventional reinforcements as well, okay, right? So next, right, so we look into the example, right? So for the example, okay, so we have example 1, okay, which requires us to calculate the ultimate moment of resistance. So the section of a pre-tension beam is stressed by 10 5 millimeters wires, okay, of 0.1% proof stress, FP 0.1K of 1600 Newton per millimeter square. Right, so you can see here, okay, it has been stated in the question, okay, that we have a section, which is a rectangular section, which is stressed by 10 millimeters, 10 5 millimeters wires, right? So instead of using cables, okay, or strands, okay, but it is, as for this section, it is provided with the pre-stressing steel wires, right? Okay, and we have 5 wires, okay, on top here. Okay, and we have another 5 wires at the bottom here, right? So you can see that as for this example, we have 2 layers of pre-stressing steel wires, right? Okay, and the proof stress, okay, so this proof stress is actually the strength, okay, of our pre-stressing steel given here is 1600 Newton per millimeter square. Right, so you can see here in the stress strain curve, right? So in the calculation, we are going to require the stress strain curve, okay, since we are going to have to determine, okay, what is the value of our proof stress, okay, then we will calculate, okay, the value of the yield stress, okay, with consideration of the partial factor of safety, okay, which is 1.15, okay, as we have mentioned just now, right? And also we are going to require to be required to have the value of E, okay, or the modulus of elasticity, right? So as for this example, okay, we have a E equals to 205 kilonewton per millimeter square, right? Okay, so you can see here, okay, we can see from the question, okay, we have if these wires, okay, are initially stressed to uh, 1120 Newton per millimeter square, right? And with 30% losses are anticipated. Okay, estimate the ultimate moment of resistance of the section if class C35/45 concrete is used. Right? Okay, so we are required to determine the ultimate moment of resistance. Okay, and we have also given, okay, we have also been given, okay, the initial stress, okay, of our pre-stressing wires, right? Okay, so what we are going to do here, okay, is that we are going to calculate, okay, for the area of the reinforcements first, okay. So as for this, okay, since we have a 5 millimeters wire, right, so therefore the area, the cross-sectional area for one wire is 19.6 millimeter square. Right, so the stress in the steel after losses, okay, can be calculated by, okay, the FOS, okay, that is due to the pre-stress force. So as for this FOS, okay, or factor of safety that we have to consider here, the value is fixed to 0.9. Right? Okay, so when we talk about pre-stress force, okay, therefore we are going to multiply, okay, the value, okay, with this 0.1. Right? Then 0.9, sorry. Right? So 0.9, okay, then multiply with the initial stress, okay, that is given in the question here, which is 1120, then multiply with 0.7. So why 0.7? Okay, we are considering the 30% of losses, right? Okay, so we have 0.7, right? So 0.9 times with 1120 times with 0.7. So here we have 705 Newton per millimeter square. Right, so that would be the steel stress, stress in steel, okay, after losses. Okay, then based on that value of 705, okay, we are going to calculate for the strain in the steel after losses, right? So as for the strain in the steel after losses, okay, we are going to calculate using this equation. Okay, whereas we have Fs, which is the stress in steel, then divided by the modulus of elasticity of the pre-stressing steel, right, which is given in the stress strain curve here, right? Okay, so we have 705 divided by 205. So we have here the pre-strain value is equals to 0.0034, right? Okay, so this value, okay, of the strain in the steel after losses has to be compared with the yield strain of our reinforcement. Right, so as for this pre-stressing reinforcement, you can see from this stress strain curve, okay, so we have already calculated the value of proof stress, okay, divided by the partial factor of safety, right? Then in order to get the yield point, okay, of the strain at yield point, okay, you can see that we can divide this 1390, okay, by the E value, right? Okay, so this value has to be divided by this and we will get the value of the strain, right? Okay, so you can see here, okay, in the calculation, we have already calculated the strain in steel after the losses is 0.0034. So in comparison to the yield strain, okay, which is 0.00678, right? So therefore our value of strain is lesser than this, right? Okay, so next part, okay, is that we are going to determine the value of the neutral axis, right? Okay, so here we are going to use the equivalent stress block, right? So the equivalent stress block that we are going to use here is similar to the RC design, okay, whereas we can see that we have this stress block, okay, with the forces, okay, that is acting for the concrete as well as acting for the steel. And in equilibrium, okay, we know that these two forces are acting in opposite directions. Okay, so one is to the positive direction, another one is to the negative directions. So therefore, okay, in equilibrium, okay, for this equivalent stress block, okay, we know that we are going to be able to write this equation in equilibrium, whereas we have Fc equals to Fs, right? So here, okay, on the stress block, okay, so you can see that we have the width of 0.567 FCK, then times with the height of the stress block, which is 0.8x, right? So this will be the FC equation. Okay, then we also have the Fs equation, right? So similar to the previous calculation, right? So in the RC design, okay, so we are going to use Fs, k equals to 0.87 kFy times with z, right? So it is actually using the similar equation, right? Okay, so a depth x of neutral axis must be found for which the compressive force Fc in the concrete is balanced by the tensile force Fs in the steel, right? So this is what is meant by the statement, right? So then the ultimate moment of resistance, okay, can be calculated using these equations, right? So we can use either Fc times with Z, or we can also use Kfs times with Z, right? Okay, so we can take Fc about Fs, okay, or we can also take Fs about Fc, okay, with the lever arm of Z here, right? So this Z here, Z equation here, okay, can be calculated using this equation of D minus with 0.4x. Okay, right. So that is for the equation for the ultimate moment of resistance. So it is actually of the same equation, okay, as what we have used previously. Right. So as the first attempt, okay, try x equals to 130, which is approximately equal to 0.5D. Right. So actually, that is a calculation, okay, that we can use, okay, in order to determine this value x, right? Okay, with regards to the stress block, okay, that we are using, right? Okay, so this is how, okay, we can estimate the x value, right? So if we go back, okay, to the question, okay, we are given the uh, proof stress, okay, of 1600 Newton per millimeter square, right? So therefore, what we can do here is that we can calculate the maximum tensile force at yield point, okay, which is Fs. So it is equals to Fp, the proof stress, okay, divided by the partial factor of safety for steel, okay, which is this one. Okay, then multiply, okay, with gamma p, okay, which is the partial factor of safety for the pre-stress force, right? So this value here is 0.9, right? So here is 1.15, right? So here is 0.9, right? And we also have the area of the pre-stressing steel, right? So as for our question just now, okay, we have 10 wires, okay, and each wire consists of 5 millimeter diameter, right? Okay, so we are going to calculate, okay, what is the area here, right? Then we are going to have here 1600, okay, which is the proof stress divided by the partial factor of safety, right? Then multiply with the partial factor of safety for the pre-stress force, then multiply with the area of the pre-stressing wires, right? So we have the area of pre-stressing wires here, right? So one wire is 19.6, so therefore 10 wires, okay, we have to multiply with 10, right? So therefore we have here 245.43 kilo Newton. Right, then taking Fs equals to Fc, okay, with in the stress block equilibrium, right? So therefore we are going to calculate here, right? So this is supposed to be 10 to the power of 3, right? Okay, so Fs is equals to 0.567 FCK times with 0.8x times with B, right? So this is the FC equation, okay, whereas we are considering the area of this stress block. So we have 0.567 FCK, then also we have 0.8x 8x, right? So therefore you have the area of the rectangular stress block. Then to relate to our section, we have to multiply the value with B, right? So that is why we have the complete equation of FC equals to this equation, multiply with B, right? Then just substitute, okay, the values that we have already calculated just now, okay, which are the maximum tensile force at yield point Fs, okay, which is 245.43 kilonewton. Okay, then equalize this with the equation of Fc. Okay, so therefore we can take out x, okay, and we have 128.83, right? So we can round up the value to become 130 mm. Right, so that is how, okay, we can actually estimate, okay, what is the value that we are going to use, right? Okay, so next we are going to calculate for the steel strains, right? So we have the equation, okay, for the final steel strain, okay, epsilon s is equals to the pre-stress strain plus with the bending strain, right? So bending strain, the pre-stress strain, okay, and also bending strain, right? So as for this, we are going to consider, okay, the layers, okay, in separately, right? So we are going to consider the top and bottom layer reinforcement separately, right? Okay, so you can see here, right? Okay, we have the first top layer, okay, whereas we are considering this equation of the pre-stress strain, okay, so this is the pre-strain that we have already calculated earlier, right? So if we look back to the previous slides, right? So we have already calculated this one, okay, which is the pre-strain value of 0.0034, right? So we are going to use the similar value, okay, for the strain after losses, okay, right? So this is the pre-strain, right? So we are going to use this. So 0.0034 plus with 175 minus with x, right? So this equation, okay, actually gives us the d value, right? So we are going to use the d value, okay, of the reinforcement that we are referring to. So as for this one, okay, since we are going for the calculation for the strains in the top layer, right? So therefore, we are going to look into the dimension towards this reinforcement, right? So this is the top layer, right? So top. So therefore, we have 300, then minus with 25, minus with 100. Okay, then we are going to get the D value, right? Okay, so that is where, okay, we get the value of 175, right? So we have 300, then minus with the nominal cover and also minus with the distance between the two layers, right? Okay, so we have 175 minus with x, okay, divided by x, right? So as for from the previous calculation, we have already estimated the value of x, right? So substitute the value into this equation. So we have x equals to 130, right? Then ECC or epsilon CC is equals to 0.0035, right? So when we calculate this, we will get 0.0046. Then we are going to compare, okay, this value with the yield strain, right? So this yield strain is obtained from the stress strain curve, right? So which is this value? So we have 0.00678. Right, so therefore for the first calculation, okay, we know that the value is lesser than the yield strain. Right, then for the bottom layer, okay, we can calculate using the similar equation. Okay, only that now the location of the steel reinforcement or the pre-stressing steel has been changed. Right, so instead of considering the top layer, now we are considering the bottom layer. Right, so therefore this 275, okay, comes from 300 minus with 25. Right, so this 25 is the cover. Okay, right? So substitute the values, right? So we have 275 minus with x divided by x, right? Then substitute the value of the epsilon cc, okay, which is for concrete, right? So this is the standard value actually for concrete, right? So the ultimate strain for concrete is 0.0035, right? So this is a fixed value, right? Then we will have here 0.0073. So compare with the value from the stress strain curve. You can see here that the value that we have calculated is larger than 0.00678. Right, okay, so if we have this kind of calculation, okay, or value, okay, so therefore, the steel stresses, okay, that we are going to obtain here, okay, as for the top layer, okay, we will be using the strain that we have calculated earlier, right, which is this one. So kita akan pakai this one, okay, whereas the value is lesser than 0.00678, right? Okay, so here we have 0.0046, okay, times with 205 times with 10 to the power of 3, right? So we are going to use this equation, okay, for the stress, right? So actually we are using this basic equation of stress equals to E equals to stress over strain, right? Sorry. So E is equals to stress over strain. So sebenarnya we are using this equation. So it is actually of the similar value, only that now what we wanted to find is the value of the stress. So we have the strain multiplied with the modulus of elasticity. So 0.0046 multiplied with E, which is 205. So we have 943 Newton per millimeter square. Then as for the bottom layer, okay, so we are going to use this maximum yield value, right? Whereas we can see here, okay, from the previous calculation is that the strain value is larger than 0.00678, which is the yield strain. So therefore, the value of the stress is actually limited to 1390. It should not be exceeding this point, right? Okay, so therefore, as for the bottom layer, okay, we are going to just use this value directly, okay, which is 1390 Newton per millimeter square, right? So as the strain in the bottom still exceeds the yield strain, right? So as what we have discussed just now. Okay, any questions so far? Boleh follow saya? Boleh tak?
Boleh, madam.
Boleh, madam.
Alright. Okay, so after we have already calculated the steel stresses, okay, then we are going to calculate the forces, right? So what we are going to do here, okay, is that we are going to compare, okay, the two values of forces, okay, between the forces that is in the concrete and also for the forces that is in the steel, okay, and what we are going to try to do here, okay, is actually to find the neutral axis that will yield, okay, Fs equals to Fc, right? Okay, so for the steel tensile force, okay, so just now we have already calculated for the stresses for the top and bottom layer of reinforcement. Okay, so we are going to multiply this, okay, with the area of reinforcement. Okay, so the area of reinforcement here is 5 times with 19.6, right? After we have already considered these two stresses, right? So we have FSA plus with FSB, okay, then multiply with 5 times with 19.6, right, which is 98, right? So you can see here we are using 943, okay, and also 1390, okay, from the previous calculation. So the steel tensile force, Fs is 229 times with 10 to the power of 3 Newton, okay, and with using the rectangular stress block, we can calculate the concrete compressive force, Fc, okay, which is using this equation of 0.567 FCKB times with 0.8x. So substitute the values and we will get here 248 times with 10 to the power of 3 Newton. Okay, so basically at this point, okay, we wanted to have the values of Fc and Fs, we wanted to have these two values as equivalent values, right? So it has to be similar. So the force Fc in the concrete is larger than the force Fs in the steel. So therefore, a smaller depth of neutral axis must be tried. So just now we are using 130. So now we can reduce the value of x a bit, right? So table 11.1 shows the results of calculations, okay, for further trial depth of neutral axis, right? So just now the first trial is 130, right? So therefore we have changed it to so this is the first one, 130. So we can reduce the value of x, okay, to 110, 120, and also 123, right? Then we recalculate back, okay, the value of the strains, okay, and also the value of the forces, right? So as you can see here, we are going to compare the value of forces, okay, and we wanted to get the values of the forces which is equivalent, right? So we wanted to have so we have when we take the value x of 123, okay, therefore we are going to have the forces of 234, okay, for both Fs and also Fc, right? So in the calculation, we are going to actually use the value of the stresses, okay? So these are the forces. So now we are going to refer to the stresses. So as for the stresses, okay, we are going to change, okay, the value of the stresses to be for the top layer, okay, it is 1000 instead of 943. Okay, and as for the bottom layer, okay, we are still going to use the same value, okay, whereas we have the value of stress at yield point. Right, so we have 1000 and also 1390, right? So in the calculation of the ultimate moment of resistance, okay, we are going to use those values, right? So we have AS, okay, which is this one, okay, then multiply with FS. So we have FS of 1000 for the top layer and we have 1390 for the bottom layer. Then multiply with D minus with 0.4x. So basically, this equation of Fs, okay, is this equation, right? So just for you to memorize, right? So we are going to use the value Fs, okay, then multiply with As, okay, Fs, As, okay, then multiply with Z, right? Okay, so this Z, okay, is D minus with 0.4x. Okay, right. So this is actually similar to if we are referring to the normal reinforcement, okay, whereas we have Fs equals to 0.87 Fyk As, right? So the equation is almost the same. Only that, okay, as for this value of Fy, right, okay, so we are going to adjust, okay, the value based on the value that we have calculated from the table. Okay, alright, so sama je the equation, okay, which is based on the stress block analysis. Okay, so 5 times with 19.6, okay, is the area of the steel reinforcement, okay, for each layers. Okay, then multiply with Fs 1000, then multiply with 1.75 minus with 0.4 times with 123, okay, which is for the top layer. Okay, then we have 1390, okay, times with 275 minus with 0.4 times with 123, right? So we have 43.1 times with 10 to the power of 6 Newton millimeter. So if X had been incorrectly chosen as 130 mm, using the same equation, mu would be equal to 42 kilonewton meter. Or in terms of the concrete, right? So if we are calculating using the concrete calculation, okay, so therefore considering X equals to 130, okay, we are going to get mu equals to 43 kilonewton meter. Right, so you can see here basically, okay, the value is almost the same, right? So it is actually not really critical, okay, if once we get the value of Fs and Fc that is close together, okay, then we can straightforward calculate for the ultimate moment of resistance. Okay, so no need to do this trial and error until you get the accurate values of Fc and also Fs. Okay, because when we compare, okay, the average of these two values, okay, with the correct answer, okay, there can only be a slight error, okay, in the position of the neutral axis. Okay, that does not have significant effect on the calculated moment of resistance. Okay, so no need to be very precise, okay, in view of getting the Fs equals to Fc. Okay, as long as the values between the 2 is almost the same. Okay, as for this, we have 229 and also 248, which is not very far apart. Okay, therefore we can consider, okay, that the X value is acceptable. Right, so what is shown here, okay, is that if we are going to calculate for the exact value. Okay, right, any questions so far regarding this first example? Boleh? Baru first example pun dah berjela-jela. Okay, right. So we have the another example, right, which is for the design of additional reinforcement. Okay, right. So for the design of additional reinforcement, okay, we are going to basically use the same method just now, okay, which is to calculate the ultimate moment of resistance. Okay, but now we are going to compare, okay, with the design moment. Right. So for the design moment, okay, we are going to compare these two values and determine whether the value is sufficient or not, okay, to cater for the design moments. Okay, so if the ULS requirements are not met, okay, the additional untensioned or partially tensioned steel may be added to increase the ultimate moment of resistance of the section. Okay, so for this example, okay, design the untensioned high yield reinforcement, okay, with FYK 500 Newton per millimeter square. Right, so when we talk about untensioned reinforcement, okay, we are going to be referring to the FYK value, okay, of a normal high yield steel reinforcement. Right, so whereas the FYK value is 500 Newton per millimeter square. Right, so for the rectangular beam section shown, which is stressed by 5 millimeters wires, okay, if the ultimate moment of resistance is to exceed the design moment of 40 kilonewton meter, okay, for concrete class for 40/50, right? So you can see here, okay, that the design moment is 40 kilonewton meter, right? Okay, so we are going to check our moment of resistance for our section, okay, with this 40 kilonewton meter. Right, then the proof stress, okay, is given as 1600 Newton per millimeter square, okay, which is similar to the previous example. Okay, and similarly with the initial stress, okay, and also the pre-stress loss value, okay, we are using the same value as for example 1, right? So this is the section, right? Okay, whereas we have the width of the section is 120. Okay, then we have the pre-stressing steel that is pre-stressing wires that is provided at the bottom of our beam, okay, with the dimension, okay, or the D value of 275, right? Okay, so as for the reinforcement that is on top here is the reinforcement that we are going to design. Right. So the first step, okay, is to check the ultimate moment of resistance. Okay. So to check the ultimate moment of resistance, okay, what we have to do first, okay, is to calculate the maximum tensile force if the pre-stressing steel yielded. Right. Okay. So as for this example, okay, since we do not have 2 layers of reinforcements, okay, so therefore we are going to calculate just once, okay, on the maximum tensile force if the pre-stressing steel yielded, right? So therefore, we are going to consider the factor of safety for the pre-stress force, okay, which is 0.9, then multiply with 5 times with 19.6 times with 1,600 divided by 1.15, right? Okay, so we have here, okay, we are considering the partial factor of safety for steel as well. Okay, then we have here 123 kilonewton. Okay, with the concrete compressive area to balance, okay, which is using the equation of 0.567 FCK times with 0.8x times with B. Right? Okay, so we are going to calculate this, okay, to determine the neutral axis depth. Right? So similar to the previous example, okay, we are going to use this basic equilibrium, K of Fs equals to Fc, right? Okay, so we have Fs, okay, that has already been calculated here, okay, on this top equation. Okay, then we also have this equation for Fc, right? Okay, so we equalize this, okay, and we will get the value x, right? So the value x that we get here is 56 millimeter. Then assuming the pre-strain is as calculated in example 1, okay, so therefore we are going to use this value of pre-strain of 0.0034, right? So it is of the same thing, the same value, okay, that we have calculated based on this initial stress, okay, and also the pre-stress losses, okay, right? So we are considering this, right? So therefore we get this 0.0034. Okay, so the total steel strain, okay, that we are going to get here, okay, is equals to the pre-strain plus with the bending strain, right? So pre-strain we have already calculated, which is 0.0034, then plus with D minus with X over X, right? So as for our example here, right, so we know that, okay, we already have the value of X determined here, 56. So therefore, we have 275 minus with 56, right? Then multiply with ECC, right? So this is epsilon CC, which is for the concrete, which is a fixed value, right? So we calculate this and we have 0.0171, okay, which is larger than 0.00678. Right, so similar to the previous equation, previous example, sorry, right, we are going to compare, okay, with the similar strain value, right? So the strain value is 0.00678, right? So we can see here, okay, that the total steel strain is 0.017, okay, so therefore we consider that our steel here has yielded, right? Then we can calculate also, okay, the lever arm, okay, since what we are going to determine here is the value of moment, so we need to have the lever arm, right? So for the lever arm, okay, we are going to calculate using this equation of D minus with 0.4x, right? So this is Z. So Z equals to D, so D is the total, okay, between the compressive phase of our section, okay, to the to the center of the reinforcement. So to the center of the reinforcement, so this is D, right? So as for Z, okay, we have D minus with 0.4x. So 0.4x is here, right? So we know that the height of our our stress block, okay, is 0.8x. So this FC force will be sitting right in the middle of the stress block, right? So therefore, okay, half of it, okay, will be 0.4x, right? Okay, so this is where we get this equation Z, okay, of D minus with 0.4x, right? So we are going to calculate that as well. Okay, so we have here 253. Okay, right. So hence, calculate the ultimate moment of resistance. Okay, so using the value of Z just now. So this is Z. Okay, then this is the value of Fs, right? So therefore, Fs multiply with Z, right? So Fs, okay, multiply with Z. So we will get the ultimate moment of resistance for our section. Okay, which is 31.1 kilonewton meter. Right, so we have to compare. Okay, this is the ultimate moment of resistance for the section with the provision, okay, of the pre-stressing wire. Right. Okay, so with this provision of reinforcement, okay, we know that it can cater up to this moment of resistance value, right, which is 31.1 kilonewton meter. So we are going to compare with the value of design moment that is given in the question, right, which is 40 kilo Newton meter, right? So this is supposed to be kilonewton meter, right? So this is the design moment, right? Okay, so for our section, okay, with regards to the loadings that will be subjected to our section. So we have 40 kilonewton, okay, which has to be catered. However, as for the section, it can cater only up to 31.1 kilonewton meter. So therefore, we are considering that our section does not have sufficient amount of moment of resistance. Okay, so here the untensioned steel, okay, is therefore required, right? So it is to permit the beam to support an ultimate moment of 40 kilonewton meter, right? So here we are going to be required to calculate the difference, okay, between the required value, okay, and also the provided value. So the required value is 40 and the provided value is 31.1. So we are lacking of 8.9 kilonewton meter, right? So those untensioned reinforcement, okay, is to cater for this additional moment, right? So we have 8.9 kilonewton meter, right? So to calculate this, okay, first we have to estimate the location of the reinforcement that we wanted to provide, right? So as for this example, okay, we estimate the depth, okay, or effective depth of the additional steel, okay, to be at 245 from the top of our beam, right? So we have here, okay, we are expecting that we are going to put the reinforcements here. So therefore, we can calculate the lever arm to the additional steel, okay, whereas we are going to calculate using this equation, right? So D minus with 0.4x, right? Okay, so we are going to get approximately 220, okay, for the Z value, right? Then the additional tension force required, okay, can be calculated since the value that we have just now is the value in moment, right? So therefore, we have to divide this by the moment lever arm, okay, in order to get the value in tension force, right? Okay, so we have here 8,900 divided by 220, right? Okay, so we have additional moment in Newton millimeter and also the lever arm in millimeter, right? So therefore, we are left with only kilo Newton, right? Okay, so therefore you can see here that we have 40.5 kilonewton. Thus, the estimated area of untensioned steel required at its yield stress is equals to 40,500 divided by 0.87 times with 500, right? So when we wanted to calculate for this area, okay, which is AS, okay, therefore we are going to use this equation because we know that Fs is equals to 0.87 FYKAS. So this is particularly for conventional reinforcement. Okay, right. So here we just substitute the value of Fs. Okay, then we will be able to determine what is the value of AS. So this AS will be the value of AS required, right? So it is similar to the RC design. So once we have determined AS required, then we can find which reinforcement that we are going to use. Okay, which diameter and also how many bars that we are going to use. Right, so as for this example, okay, we are going to use 10 millimeter diameter bars, okay, with and we are going to select two numbers of bars, okay, because we know here, okay, that we have the value is 93, right? So therefore we are choosing 2H10, right? So 2H10, we have two bars, okay, with 10 millimeter diameter each, with the total area of reinforcement, okay, of 157 millimeter squared, right? So you can calculate this yourself, okay, or you can also refer to the table, okay, of reinforcement, okay, for this value of the cross-sectional area of bars. Okay, so once we have determined the value, the reinforcement to be provided, what we have to do next is that we have to check for the steel strain, right? So since just now we already have the additional steel, right? So therefore we have to calculate the strain for both reinforcements, okay? Right, so if additional steel has yielded, the force into H10 bars, okay, will be 157 times with 500 times with 10 to the power of negative 3 divided by the partial factor of safety, okay, which is 1.15. Okay, so basically, okay, what we are calculating here is Fs, right? So what you have to do is just to substitute this value of As, right? Okay, so we have 0.87, which already considers the partial factor of safety. Then we have FYK 500, then times with AS, right? So AS must be the AS that we have provided, okay, right? So AS that we have provided is higher than the required value, right? So we have here 68.3 kilonewton. So therefore, the total tensile force, if all the steel has yielded, okay, will become 123 plus with the with 68.3, right? So we have the total tensile force that is due to the pre-stressed steel, okay, and also the tensile force that is due to the additional steel, right? So in the checking of the strain, okay, we need to consider both. So thus, okay, the depth of neutral axis, okay, at ultimate, okay, will become this one, okay, whereas we are going to recalculate the x value with the basis of Fs equals to Fc, right? So here, okay, we are going to use similar equations, okay, and we are going to consider this value of 191.3 kilo Newton, okay, and divide this, okay, by the Fc value, okay, so this is the Fc equation, okay, and we are going to determine the value of x, right? So this is actually the new value of x, okay, in consideration, okay, of the pre-stressed steel and also the additional steel, right? So we calculate the new value of x. So we have here 88 millimeters. So therefore, okay, the pre-stressing steel steel strain, okay, is equals to 275 minus with 88, right? So this 275 is the D value. Okay, then this 88 is the X value, right? Okay, so multiply with 0.0035 plus with 0.0034, which is the pre-strain value, right? So you can see here that we have the calculation, the strain, okay, for the pre-stressing steel strain of 0.0108, right? So we are going to compare, okay, this value with the yield value, right? So we know that previously, okay, from the stress strain diagram, okay, the yield point is 0.00678, right? So the value that we have calculated here, okay, shows that the pre-stressing steel has yielded, right? Okay, whereas the value is larger, right? So this is actually the requirement, right? So when we do this checking of the steel strain, okay, we must ensure that our reinforcement yielded, right? Okay, so this is the first one, which is for the pre-stressing steel strain. Okay, so the pre-stressing steel strain is the steel that is sitting at the bottom of the beam. Okay, then the second one is for untensioned steel strain. Okay, so the difference here is actually is only on the value of D, right? So here, this is the D value with the location of 2H10. Okay, and also you can see here in the calculation for the untensioned steel strain, we do not have the initial pre-strain value, right? So this initial pre-strain value is particularly for the pre-stressing steel only, right? So when we are considering the additional steel strain, the additional steel, okay, or the untensioned reinforcements, okay, so therefore we do not need to add up with that value of 0.0034, right? So we have this value, okay, so 245 minus with 88, okay, divided by 88 times with 0.0035, right? So it is equals to 0.0062. And as for this value for the untensioned steel strain, okay, since it is considering a higher steel, right? So therefore the stress strain curve must also be the higher steel stress strain curve, right? Okay, whereas we can see here we have FYK of 500. Okay, so we can divide this, okay, by the partial factor of safety, which is similar to the pre-stressing steel. Okay, as long as it is steel, therefore the partial factor of safety is fixed to 1.15, right? Okay, so therefore we have FYK divided by 1.15, then divide by 200 kilonewton per millimeter square, and we will get the yield strain of 0.00217, right? So that value of 0.00217 is actually at this point, okay, which is here. Okay, so it is 0.00217, right? So it looks almost the same as the previous stress strain curve that we have seen, only that that is for the pre-stressing steel. Okay, right? So here, okay, we have 0.0027, which is to be compared, okay, with the steel strain that we have provided, right? So here is 0.0062, right? So this is also greater than the value of the yield strain, right? So we know here, okay, that both values of the steel strain, okay, exceeded the yield point, right? Okay, so for the to meet the requirement, okay, both steel strain, okay, both strain values, okay, must have yielded. Okay, it is not stress. This is supposed to be strain values. Okay. Right. Then the last one, okay, is to check back the ultimate moment of resistance. Okay, so once we have already determined the x values, okay, then we can just substitute into the equation. And we have here mu equals to 123, okay, times with 275 minus with 0.4x. So that is for the pre-stressing steel. Then we have 68.3, okay, plus with 68.3 times with 245 minus with 0.4x. So this is particularly for the 2H10 reinforcement. So therefore we have the ultimate moment of resistance of 43.8 kilonewton meter. So we have to compare back, okay, this ultimate moment of resistance, okay, with the design moment, okay, that is provided in the question, which is 40 kilonewton meter. So now we know that the ultimate moment of resistance of our section here exceeds the design moment, right? So therefore this satisfies the requirement. Okay, right? So this satisfies the requirement of the ultimate moment of resistance. Okay, so if it had been found in B that either the pre-stressing steel or untensioned steel had not yielded, then a trial and error approach similar to example 1 must have been necessary, right? Okay, so this is where this is mentioning about these two steel strain. Okay, so if either one, okay, of these two has not yielded, right, therefore we have to make adjustment on the x value, right? Okay, so as for the previous example, okay, we can make adjustment on the x value in order to get the fs equals to fc, right? So similarly for this part, okay, if the steel strain, okay, or either the pre-stressing steel strain or the untensioned steel strain does not yield, okay, it means that this strain values is lesser than the yield strain. So therefore you have to do the trial and error, which means you have to determine the new value of x. Then only you can proceed to the checking of the ultimate moment of resistance.